Somewhere in a drawer, there is a metal that can turn into liquid in your hand. Not with a torch, not with a chemical reaction, just body heat. That metal is gallium, and it breaks nearly everything we assume about what metal is supposed to be. At room temperature, gallium looks completely ordinary. It is a dull, silvery solid, cool to the touch, dense, seemingly as stable as a chunk of steel. But its melting point sits just below normal body temperature. That means the moment you close your hand around a piece of gallium and hold it, your skin is warmer than the point at which its structure gives way. Keep holding it, and the solid begins to slump, first softening at the edges like wax near a flame, then sagging under its own weight. Given enough time, that same block can turn into a silvery puddle pooling in your palm, still faintly warm, still recognizably the same substance that felt so solid a few minutes earlier. It feels like a magic trick, because we have been trained our whole lives to think of metal as the opposite of fragile. Metal is what furnaces are for. Metal needs fire, sparks, blast heat measured in the thousands of degrees to become liquid. Gallium erases that rule using nothing but ordinary human warmth. No flame required, no special equipment, just contact. That strange behavior is not only a party trick, though. Gallium plays a real role in modern technology. It is used in electronics, in semiconductors, and in a range of special alloys, precisely because its odd properties make it valuable in ways ordinary structural metals cannot match. It shows up in components engineered to be small, efficient, and reliable, hiding inside devices people use every day without a second thought about the metal that makes them work. But gallium also has a mischievous, almost destructive side. If it comes into contact with aluminum, gallium can slip directly into that metal structure. Once inside, it does not just sit there quietly. It weakens the aluminum from within, working its way between the bonds that give the metal its strength. An object that looked solid and dependable can turn brittle enough to crumble apart. That is exactly why gallium must be handled carefully around aluminum objects. A stray smear of liquid gallium can quietly ruin equipment that took real engineering to build. Step back, and the real lesson here is not just about one strange element. It is that metal was never one single personality. We tend to lump every metal into a single mental category: hard, cold, unyielding. But the periodic table does not work that way. Mercury is liquid at room temperature, flowing and pooling like water despite being chemically, unmistakably, a metal. Sodium is light enough to cut with a knife, even though it is also dangerously reactive. And gallium sits in its own strange spot, solid enough to hold its shape on a shelf, liquid enough to melt from nothing more than the warmth of human skin. Why does one element behave so differently from another when they sit right next to each other on the same chart? The answer is not found in size, or color, or where a sample came from. It is found at the atomic level, in how atoms are built and how they bond to their neighbors. Change those details even slightly, and the resulting material can behave in a completely different way. Two elements can sit side by side on the periodic table, look almost identical in a photograph, and still behave like strangers once you actually pick them up. Tiny differences in atomic structure can create wildly different behavior in the world we can actually touch. The difference between a metal that stays solid inside an engine and one that dissolves in your palm the moment you close your fingers around it. That is why the periodic table is less like a list and more like a set of hidden rules, rules that quietly decide which materials will be hard, soft, reactive, or docile long before anyone tests them by hand. Gallium happens to be the element that turns those hidden rules into a magic trick you can actually watch happen. A cold-looking metal, sitting still and solid, becomes liquid from human warmth alone. It is a small reminder that ordinary categories, like solid and metal, are not as fixed as they feel. Follow for more random things you may not know.